So yeah, welcome to the talk, the last talk of this conference. Let's hang in for 40 more minutes. Hang in there. Okay. Yeah. So my name is Asim. I work on Greenplum. I am an engineer. I write code and test it out as well. So the last part is important, and sometimes it is the other way around. I write the tests first and then write the code to make the tests pass. So this is a typical development philosophy followed at Greenplum, which is commonly known as test-driven development. And why we are talking about this today is because fault injection facility it facilitates writing tests which are otherwise very complex and very hard to run in a reliable way, in a repeatable way, right? So let's see what we are going to talk about today. First, we will go through existing test frameworks that a typical Postgres developer has has at their disposal. And then we will see some test scenarios which are otherwise very difficult to, if not impossible, to write using what we have already. And that's where the need for something like fault injection comes in. And then we will go over the fault injection proposal, which is already submitted on the hackers mailing list. The patch is out there. And then we will write a couple of tests using the fault injection facility. Okay, so the first framework that we are going to briefly talk about is the Regress Framework. So if you go to the source repository and look at src test regress, you will see a bunch of tests, and those tests are written as SQL commands, and each SQL command has some output, right? So each SQL file, which is a set of SQL commands, has an expected answer file as well. So a test writer typically writes this set of SQL commands, runs them against the system under test, which is Postgres instance, and then generates an answer file, manually inspects it if it is okay, and then freezes it as the expected answer. And then what happens is any change that is made to the Postgres code base, the same set of SQL is run, the results that are generated are compared against the answer file, and if there is a problem, then that test fails if the results do not match. Pretty simple. And it is so for example, if you write your own maybe a planner node or a different alter table command, right? So you compile the source code with your changes, run the Postgres instance, and write a test for that alter command using this Regress framework. Very neat and fast. The next one is isolation framework. Now this is useful when you want to test concurrency scenarios, a couple of sessions, one or more sessions running concurrently and interacting with each other. So with this framework, you can achieve a somewhat specific interleaving of concurrent sessions. And we will see more about this. So each session is defined as a set of steps, and a step can have one or more SQL commands. And then finally, the test is nothing but a permutation of the steps that are defined, and each step has a label. So let's look at an example to get a better idea. Yeah, it's not too small, right? You can read it, hopefully. So yeah, what we are seeing is a very simple isolation spec. We call a test written in this isolation framework as a spec file. And that spec file, as this particular spec file contains two sessions, S1 and S2. And S1 session comprises of an alter command, and S2 is simply a select. And you can see that session S1 has 2 steps defined, and the alter 1 and commit 1, these are the labels for those steps. And at the end, the last line has, you can use those the labels to the steps to define a permutation, which is what you see on the last line. So what this means is the test runner would execute the SQL statements exactly as identified by the permutation. So the test runner would create 2 sessions against the Postgres instance that is under test. It will, in one session, which is S1, it will run alter 1. In the second session, it will run select 2. And as you can see, alter acquires access exclusive lock on a table, so the select 2 would have to wait until the alter finishes, right? And then in the first session again it will commit, and once the first session commits, the second session, which is select 2, will go ahead and get the results. And this, so any questions so far? Like, is this clear enough? Okay. And even for this test framework, we have an expected answer file, right? So the answer file comprises of the results of the SQL commands that are executed by a permutation. And within a spec file, you can have as many permutations as possible for the given steps. And you can have as many sessions as you like in a spec file. Okay. The third test framework, and this is the last one out of the existing test frameworks, is that it's called as TAP, and I do not know what TAP stands for. But it is a Perl-based test framework, and it is, because it's Perl-based, it's much more powerful. You can express a lot of things, and it is currently used to test different scenarios which are not really SQL commands, but they are a functionality of the database. For example, initializing a standby, or initializing the database for that matter, initdb, or backup or restore, setting up streaming replication. Or you can have some fancy things like kill a backend with SQL and do crash recovery and see if the things are sane after the crash recovery is complete, right? So this is a much more expressive test framework, and it involves learning curve because you have to know Perl, which I did not. Okay. So yeah, we've got through the brief overview of the existing test frameworks, and now let's think about some scenarios. So the first one is bring down a synchronous standby while a master backend waits for commit LSN to be flushed. Now what that means is, let's say you have a standby and a master, and the standby is synchronous. So the replication is synchronous, and by synchronous, by definition, what that means is a commit that happens on master waits, the commit is not complete until the standby confirms that the commit LSN, LSN is log sequence number, meaning the wall write ahead log, until the commit record has been flushed by the standby. Okay, so the commit will keep on waiting until the standby confirms that it has flushed wall up to the commit LSN. This is the definition of synchronous replication. But what happens if if a transaction has written a commit record locally on master, and it is waiting for the standby to for a confirmation that it has written the commit record, and during this exact point the standby goes down or the replication breaks, right? At no point it should happen that the commit should be, the transaction should move on without the confirmation from standby, because the replication is configured to be synchronous. But do we have a test for it? Or how do we write a test case which is repeatable for this scenario using the existing test frameworks? right? Even the tap framework, which is much more expressive, is not sufficient for writing such a scenario. Let's look at another scenario. Server crash after writing commit wall record, but before updating the commit log. So this is when a transaction commits, a whole bunch of things happen, right? One of the most important things is a commit wall record is written to the disk. And then the other most important thing, the second most important thing is the commit log, which is a separate log, is updated with the status of this transaction, that this transaction is now committed, correct? So between these two intervals, these are two separate disk writes, right? What happens if the server crashes after the first commit, after the commit wall record has been written, but before the commit log has been updated with the transaction status? So upon crash recovery, everything will be fine, and it is really the case. But don't we think that we should have a test case to cover this scenario? Because as and when new changes happen to the server code base, we don't want to regress in this particular case, right? So again, this scenario is also very difficult to implement using tap or regress or isolation framework, right? Because how do you let a backend halt after writing commit record and before updating the status and then crash the server? So it's very hard to get this thing. Let's look at another one. Streaming replication behavior when the replication connection breaks intermittently. And this is, so the idea is, if the streaming replication is set up and because of some network blip, there is a problem and the connection breaks for a short duration and then it gets re-established, right? On the standby side, the standby keeps on reconnecting, keeps on trying to connect if the connection breaks. So because of network blip, if the connection breaks and the standby makes another attempt to establish the connection and that succeeds. So in this event, we should not have any changes to the synchronous, to the replication behavior. And what we have seen, and this is a genuine bug which is already discussed on the mailing list, is that if the standby is having, if a lot of replay lag has been built on the standby. Now replay lag meaning the standby is doing two things, right? One is it is continuously receiving the changes from the master, receiving the changes in terms of wall records, wall stream, and those changes are written to disk. And the second process on the standby is continuously replaying the changes that have already been written to disk, so that the standby data directory becomes in sync with the master data directory. And it is a common scenario that the replay lags behind, because on the master you have concurrent sessions writing to the write ahead log, but on the standby there is only one replay process that is replaying the wall. So you must have seen in practice that the standby falls behind. And if the replay is lagging, if the standby is lagging and the replication connection breaks, and if you have synchronous replication set up, then there are some interesting changes that happen when the replication connection is re-established. And that's a genuine bug, which is, as I mentioned, it's already been discussed on the mailing list. We have a patch to fix it. But again, the reason I'm mentioning all this is this particular scenario is also, as you can see, very tricky to implement using any of the existing test frameworks that we already have. Yeah, Ashutosh. Yes, that's exactly true. And fault injection is an extension. So you're absolutely correct. So yeah, a couple of more scenarios. Just throwing it out there, there are too many things that are complex to implement using the existing test framework. Group commit is another example where you have to have multiple transactions lining up to update the commit log status. It's a performance optimization, but how do we guarantee that this performance optimization is taking place in presence of concurrent transactions? So these things are very hard to implement using the existing test frameworks. And primarily because the existing test frameworks are SQL based, right? You need to rely on locks to be able to synchronize the two or more concurrent sessions. Was a syscache or relcache entry utilized, or there was a cache miss? This is another scenario we don't know. I mean, how do we test if or guarantee that a syscache was being used? And if you have written some significant code, or if you have played around with Postgres codebase, you can also think of some scenarios pretty easily that are hard to test. So yeah, hopefully with this, I think we all are convinced that we need something more than what we already have, right? And that is fault injection. So one option that we are trying to provide is fault injection. Now, fault injection involves defining a fault point. And a fault point is nothing but a location in the source code that is labeled as per the test developer, right? So its fault point is nothing but an interesting point in the source code. And the idea is when the point in the source code is reached during execution, a certain configured action will be taken in place of just executing that line of code, right? So that's what is basically the idea. And this involves changing the source code. So we have added a preprocessor flag, which is labeled as fault injector, and there is an extension that allows for SQL that provides an SQL interface to enable a pre-configured fault. So in order to create a test case using fault injectors, you need two things. You need to modify the source code and define the fault point, and you need to write a SQL statement that will enable the fault point. And all of that, so the enabling of the fault point can happen using any of the existing test frameworks, which is PG Regress, Isolation, or TAP. And internally, the way it is implemented is we use shared memory, Postgres shared memory, to remember the faults that are enabled during testing. So when a fault point is reached during execution, if the fault is enabled, well, the way to identify whether the fault is enabled and the action should be taken is to look at the shared memory and see if the fault is enabled. If it is enabled, then the corresponding action, the action is also recorded in shared memory, and that action is taken. And we have a patch for this, so feel free to check it out. So let's take a look, delve deeper into how it works. So what you see on the screen is a definition of heap insert fault. Heap insert is just a name that I have chosen, but it's a good idea to name it according to the function that function or some name that indicates the purpose of the fault, right? So in this particular case, as you can see, the heap insert function is changed, and right at the beginning we have added this fault called heap insert. So this is how a typical fault definition looks like. And you can, besides fault name, there are two parameters that we should talk about. One is the database name, which is empty in this particular case, and the other is the last parameter, which is get relation name, which means which is helpful to qualify the fault triggering for a particular table in this case. And we will see in a moment how that works. And this is the SQL interface to inject a fault. So in this particular case, we are, as I mentioned, this is an extension. So first you need to create extension, fault injector, and then you need to invoke a function called inject fault, and that would result in the fault heap insert, which is predefined, being enabled. Okay. So in this case, the error argument indicates that the action taken after this fault is hit would be abort the transaction with elog error. And the last argument, my table, that's the table name, and that's where the fault triggering can be even more qualified. So a subsequent insert. So once this select inject fault function is executed, thereafter the backend process that is executing heap insert, if it executes heap insert subsequently, then and the insert is happening on a table which is named as my table, then the fault will be triggered, which means the error action will be taken and the transaction will be aborted. This is how it works. Any questions or comments or something not clear? Okay. So fault actions, there are a bunch of fault actions that we can encode. Error that we have already seen. There is a skip action, which means literally do nothing, and it is useful to remember that a particular location in the code or a particular function was called, for example, or a particular branch was taken. So this is useful for that, or it is also useful to have some custom logic when a particular fault is hit. Then there is suspend and resume. Reset. Reset means to remove the fault. So in the shared memory, once you inject a reset fault, the shared memory will be cleared and the fault will no longer have any effect. And status is how many times a fault is triggered. So let's take an example of this, one more example of a skip fault. So in this case, we've modified create checkpoint function in the checkpointer, and at the beginning of the checkpointer function, create checkpoint function, we have defined this fault which is named as checkpoint, and it's a skip. So if the fault was injected with a skip action, then what would we do is the custom logic that we would perform is to skip the checkpoint. And this is useful to test certain crash recovery scenarios. If you want to test replay of a particular wall record that you want, you don't want checkpointer to interfere in between your tests. So this is a way to let the checkpointer skip checkpoints. So going back to heap insert fault, we will have, so a few more interfaces that we have is wait until triggered fault. So this is also an interface provided by the extension, which means that the test will block here at this statement until the backend process executes heap insert fault, until some backend process executes heap insert fault, and that gets triggered exactly one time. So the last argument 1 means it will wait until the heap insert fault is triggered one time. And remember, the fault action and its status, everything is maintained in shared memory, right? So whenever the fault is hit, all other backends know that the fault is hit, and that's why this works. So the other interface is status that we saw. It gives you in table format. It returns a text indicating how many times a fault is triggered and what is the whether it is complete or not. And the last one is reset, which is to remove the fault. And this is interesting. So in a synchro, if you have streaming replication setup, so this interface comes in handy, where if you know the port number that the standby is listening on, port number and host name, then you can use this interface to inject a fault on the standby. Now, this example is rather incorrect because heap insert will never be executed on standby. Standby is read only, but you could have some, you could define a different fault and inject it on the standby using this standby host and standby port. So what internally happens is this function would establish another libpq connection and execute and enable this fault on the standby. So the standby shared memory will have the fault as enabled, and it will be triggered on the standby. Yeah, so fault status is you have triggered, which means it was reached during execution by some backend process, right? And the action was taken. Injected but not triggered means the test has executed inject fault, but the fault has not been reached during execution by any backend process. Completed means it was the fault, the backend, some backend process reached the fault and the action was taken, it was triggered, and the maximum number of times it was triggered, so it will no longer be triggered. Meaning even if another backend process reaches that point, no action will be taken. It will continue as if nothing was, no fault was enabled. Oops. Yeah. So enough of theory. Let's write some tests. Let me do a time check. How much time do we have? Yeah. Yeah. Okay. So this is going to be interesting. This is the first test that we are going to write is a speculative insert test case. And you have seen this insert into on conflict command, right? Have you used this before? Insert on conflict. It allows you to do some other action if there is a constraint violation during insert and so on. So the test specifically that we are going to write involves of course a conflict during insert on conflict, but those conflicts are detected at a particular point, and that point is when the insert has updated the heap tuple, heap table, but it is yet to make the corresponding updates on an index, and that's when the conflicts are detected because of a concurrently running transaction. And there is a test for it already committed in master, and that test is you can check it out, and to be honest my head hurts looking at the test because it's so complex. It uses advisory locks and goes on and on, and if you look at the discussion on the mailing list, the test was developed through several iterations. The first draft, it seemed it was okay, but after let's say 10 runs it would fail intermittently for 4 times. So it's very hard to get such a interleaving of transactions reliably, right, in a repeatable way. So you need something like fault injectors, and let's see, let's try to write this test using faults. So there are, looking at the problem is clear, right? We want to achieve an interleaving of concurrent transactions such that one transaction is executing insert into on conflict, and it has completed inserting the tuple into the heap table, but it is yet to insert, it is yet to update the index, and that's when we want to suspend the transaction, right? So we can use suspend fault here. So let's first look at the setup. So it's just upsert test is the table name that we have chosen. We create a unique index on it so that the conflicts are generated, and then we define 2 faults here. One is the suspend fault that we just talked about, which is the name of this fault is insert index tuples, and this is, there is a function with exactly this name, insert index tuples, which is executed right after the fault, right after the a tuple has been inserted into the heap table, and this function updates the index. So we suspend the, we inject a suspend fault which is at the beginning of this function, right? So no action will be taken until the fault is resumed. And we inject a second fault, we need another fault, which is heap insert speculative, right? And this is again a function, and you can, so the purpose of this fault is that the speculative action was, on conflict action was taken. So this allows us to determine that an on conflict action was indeed taken, because it's a skip fault. No action, no action will be taken when this fault is hit, but only in the shared memory its status will be recorded, and later when we check the status we can determine that this fault was hit, and then the test can figure out if it should pass or fail, right? So we have 2 faults and a table and an index defined. So as you can see here, the syntax resembles the isolation syntax that we saw. So this is an isolation test case, and we have 2 steps defined here. and both the steps S1 upsert, S2 upsert. I'm sorry, we have two sessions defined here. So these two sessions, this is not a complete spec file. I have just included a snippet for better readability. So what we have is two different sessions, and both of them are doing insert into on conflict command. Both of them are executing this. Okay, and so there is another step which is to inject a resume fault, which will be executed in another session. So in isolation, remember that you can have multiple sessions. So in this particular spec file, we have at least two sessions here, and then the resume fault would let the suspended transaction move on and update the index. So this is not a complete spec, but you get a brief idea of what's happening, right? So let's see the permutation. So S1 upsert and the ampersand and, that's a new enhancement that we have added to isolation framework, which allows the isolation framework to determine that this particular command is going to block, and the reason for blocking is something other than locks. Because today the isolation framework, if a particular command ends up blocking, and if it blocks without for some other reason than waiting on a lock, it will just fail the test. So we had to add this, we had to teach isolation framework that there is another reason for a command to wait. So S1 upsert, remember what is S1 upsert? It's just the insert on conflict action, right? So this step is going to wait because we have injected the suspend fault. Yeah. So S1 upsert is going to block because of the suspend fault. Then we do S2 upsert, which is again insert on conflict, but from a different session, right? And as you can see, this session should succeed because there is no reason this will block, because the previous transaction has not committed yet, right? Although it is inserting some conflicting tuples, the transaction is still in progress, so its effects are not seen by the S2 upsert step. So S2 upsert step is expected to complete without conflict, and then we unblock S1, and then it detects the conflicts, right? And the last but one step, which is S1 fault status, that allows us to validate that the speculative update, the conflict resolution step was taken, and then we run a select to determine the correct results that were finally ended into the table. So yeah, this is how simple it looks like. And if you have time, do take a look at the other test that I mentioned here, which is currently committed on master. This one, it's very complex. So yeah, this is our speculative insert test case. Okay, we have one more test to write, but less than 10 minutes. So let's rush through. Unless you have any questions on this particular test. Okay. The other test is streaming replication test, and it relates to the bug that we talked about earlier during streaming replication. If you have synchronous replication set up, right, and there is a replay lag built up on the standby, and the replication connection breaks and it is re-established, what happens is the commits keep blocking on master until the entire replay lag is finished, until the standby finishes replaying all the wall. And that's wrong because then if you had synchronous commit set to remote write, after disconnection, suddenly the behavior is as if synchronous commit guck is set to remote apply, right? What ends up happening is after the disconnection and re-establishing the connection, commits on the master keep waiting until the entire replay is finished, and that's the bug. So let's write a test case for this. There is a discussion already on this problem on the hackers mailing list. So here is the setup. We have a master running on 5432, the default port. We have a standby running on 5433, and the synchronous replication is set up between master and standby. And we are going to write a regress test for this, PG regress, the simple SQL based test, no isolation, no interleaving of concurrent transactions. Okay. So what faults do we need for this? First is we need to induce replay lag, and for that we need a fault which would suspend the standby replay process, right? There is already a GUC called recovery min apply delay, but that's not helpful for us because we are writing a PG regress test, and through SQL interface there is no way to change a GUC on a standby, right? So let's use the remote fault interface to induce this delay, and then we need another fault to terminate the connection, terminate the replication connection. Okay. And as I mentioned earlier, the logic on the standby is that as soon as the standby detects that the connection is broken, it tries to re-establish the connection. So we don't have to do anything after disconnecting. The connection will be re-established by the standby. So let's look at the test. This is again a snippet from the test case, not full complete test. So I hope this is large enough. Select inject fault, redo main loop, and sleep. Sleep is the type of fault we are using here, and the number 10 is the seconds to sleep for. So what this means is once this fault is injected, the standby will start sleeping before it applies a wall record in its main loop, right? So after injecting the fault, and by the way, the localhost and 5433, these two last arguments indicate that this is a remote fault, and it will be injected on the standby. And then you have we have this insert command which will generate a wall log on the master. So replaying this wall will cause the standby to sleep for 10 seconds, and then we kill the standby. So through another fault again, we kill the wall sender, wall receiver process, so that the replication connection is broken, right? And this is the fault again. So to wall receiver loop, in the wall receiver loop, we inject a fatal fault, which means that the wall receiver will exit with a fatal, and the standby postmaster will restart the wall receiver process, and the replication connection will be re-established. And the last part is the validation step. So the last insert statement tries to insert into the table with a timestamp, which is now, right? So the value that gets inserted in this table is the timestamp at which the insert command was executed, and if the insert command ended up waiting until the replay finishes, then if we do a select and compare the current timestamp with what was inserted into the table, we can determine that the replay process ended up waiting, the commit ended up waiting for the replay. But the expectation here is if we do a select after this insert and compare the timestamp again for select now minus what is recorded in this table, if we do this, then the difference should not be greater than 10 seconds, right? Then if it is greater, then the test should fail. So yeah, that's how it looks like. It's a simple PG regress test that allows us to test the fairly complex scenario and manifest the bug. That's it. So that's all I had. Please help review the patch. Thank you. Any questions? Yeah, please.
So have you gotten, this looks wonderful, thank you.
Sure.
This looks great. So have you gotten any encouragement, pushback? How's the patch process going?
Yes, so our dear friend Mikhail Paquier has reviewed it. Thank you very much. And he thinks it is too intrusive. So yeah, that's where it is stuck at this point. Yeah.
because you've discussed, I believe you are a dev.
Yes, yes.
So when these patches are committed, is this like you raise a pull request? Can they show up in another branch?
No, we use mailing list.
No. Once, see, you're making a commit, right? Or you're making patches available. So do they show up as pull request onto the master?
No, they don't. So the way it works is you submit your patches on the mailing list.
That's fine.
Yeah,
so
and that's it.
So effectively, if there are like 10 devs on the PostgreSQL community, maybe company sponsored, when they make patches available, if anybody clones out the master, they will not get those experimental patches, right?
No, they will need to look at the mailing list and download the attachment and then apply the patch.
So don't you think that is something very anachronistic compared to what many other very flourishing communities do, where they leave this as explorative patches, so the community members can decide rather than running around looking all over the mailing list?
Yeah, we can discuss this offline. This is not related to the
patch.
Yeah, there are lots of opinions on this topic within the community. So, yeah.
Laughing at the situation.
Yes, and totally agree. This is a retrograde process, but this is how it is. Yes. Correct. Yeah. Oh yeah, thank you for asking that question. This is already in Greenplum. We use this all the time, and in fact, this we last year at PGCon Ottawa. One nice thing at Ottawa is there is an unconference day. So during that unconference, we ended up discussing fault injection, exactly this problem, but in a very informal setting, and we tried to showcase what we have on the Greenplum side, and there was significant interest in the community for fault injection. Therefore, we went and ported the patch from Greenplum to Postgres and submitted the patch. This has already been there, Greenplum 6, 5, yeah. Yeah. No, so this fault injection is streaming, everything is available in, so streaming replication we use for master and standby in Greenplum for like since 4 or 5x, and for the fault injection has been there since beginning, like even before I joined, we have been using fault injection for writing tests at Greenplum. So.
All right, those are all of the questions. Thank you. Thanks, Asim. Thank you for those insights.
Thank you.